Hi there. In this recording, I want to discuss um, momentum exchange in fluids and how the Bernoulli formula is visualized in PySpace. So I've already described in the document, the PySpace theory document here, the momentum interaction diagrams. This section refers to the uh, to the to the case where Johann Bernoulli I've realized that when you increase the velocity of a fluid, when you increase the velocity of a fluid, it's going through some kind of a constriction, and the pressure drops. So, so the use case is as follows: you have a higher pressure in the intake part of the tube. You have a fluid in the pipe, and then it hits a constriction, and the pressure becomes low, but the velocity speeds up, and then once it goes out of the constriction, we get high pressure again. The way that Bernoulli formalized this in classical physics was he said that the conservation of momentum was maintained, and he basically formulated it in terms of the velocity, in terms of the pressure, and in terms of the gravitational pressure, the gravitational field that the pipe is in. So we're assuming that we're running, uh, in this case, parallel to gravity. So the gravitational field is the same at all points. But you put this in because this is required depending on the kind of problem you're trying to solve. But basically, he said it's a constant. So he said if you have high pressure here and you've high low and you have a smaller area here, you have to get low pressure in order, because it's a constant. Now, the thing about this formula is that although the formula explains it mathematically, it isn't very intuitive. A lot of people naturally assume that as the liquid enters the constriction, that somehow it sort of kind of gets more blocked, and it therefore the pressure should get higher, yeah, and it should slow down. And yet, when people read the research done, it was the other way around, and people I think find it kind of confusing. But when you explain it in terms of the conservation of momentum, then you can say, okay, that makes sense. Now, the thing is, in PySpace, it's possible to visualize this actual case. So what you do is you can use a momentum interaction diagram. It's pretty simple. It's this one over here. So the idea being that you have the relative observer, which is the stationary partial, the area loss due to movement, and then the actual movement of the object itself. This example is just to show a rocket, but this is just a kind of like a template to give you an idea of what each piece means. Now, in this case, we're not talking about a rocket or anything. We're talking about two fluid particles entering some kind of a constriction, which is here, and they have to basically go through the constriction. So it's a kind of a simplified example where you have two molecules of a fluid entering some kind of a constriction, and then you get this third particle, which is one of these other two, and it's here. It's the so basically, what we have is a situation where these two particles have momentum. So the blue area here is the momentum. The line here is the velocity line. So this is the velocity line. The large pi shell is the observer. This is the area loss, which is the momentum, and this is the particle itself, and this is the particle and the momentum. So they both have to go into this constriction, but we have to conserve momentum. In other words, we have to combine the momentum that's here into this area here. So we basically add it to this pi shell, this other particle. In other words, the momentum is getting transferred into the constriction, and it's got to be conserved. So you have to give each particle more momentum. Alright? Now, that's what the blue area means. So in other words, you've increased the momentum on this particle. It gets smaller, which is the way the PySpace theory works. The velocity gets higher, and because the particle is smaller, that's the physical particle, the pressure drops. So in other words, it moves faster and it has lower pressure. and it is here it's moving slower, and it has higher pressure because the particles are bigger. And that's how to describe the Bernoulli uh, fluid law in pi space. So I'm hoping that will be more intuitive. If you think of momentum as this blue area, it gets added to this and becomes more momentum, it moves faster, and the pressure is lower. And that's it. It's that simple. Thank you.